couple things. I've been getting lots of questions in office hours about like, how do you know if it's separable? How do you know if it's going to be linear? Linear is easier to spot than separable. Separable always requires us kind of like doing some algebra to mix things up. So if I'm looking to check if it's linear, I find the variable that's got the derivative, and then I look for anywhere else that that variable shows up in the problem. And because the y shows up here inside of a cosine, that's definitely not linear. I would need it to show up just as like a y by itself to the first power somewhere. Since it's not linear, we're hoping it's separable because that's the only other kind that we're actually able to solve. So I'm going to swap out my y prime for dy dx. And then the whole idea behind separable is that I'm going to get my x's on one side, my y's on the other. And we could have a different letter, but in this case, we're just working with x's and y's. I never get a choice of which goes on which side, because I can only integrate with the d something part in the numerator. So I've got to multiply both sides by dx. And that means that my x's are going to be on the right and my y's will be on the left. So if I divide both sides by cosine squared y, this is where my hint kind of comes into play. The only way I know how to integrate this is to rewrite that cosine squared as a secant squared. So this side looks like secant squared y dy. And over here, I've got x cubed dx. Luckily, secant squared is somebody's derivative. Whose derivative is it? So I've got tangent of y is equal to 1/4 x to the 4th plus the constant. And you could choose to solve this for y first. I think it's going to be easier for us to plug in the point first because we have an initial condition here. Notation wise, that 1 means that we're letting x be equal to 1 and we're letting y be equal to 0. So I'm looking at tangent of 0 is equal to 1/4 of 1 to the 4th plus a constant. And tangent of 0 is 0. So 0 is equal to 1/4 plus c, which means that I know that c is negative 1/4. Now don't forget this last step. The last step is to actually take that c and put the whole thing back together. So we solved for our c when it looked like this, when we had the tangent of y is equal to 1/4 x to the 4th. I'm going to put in my minus 1/4 for c. But if I solve to get y by itself, that's going to look like y equals tan inverse of all of that stuff. The whole idea of Euler's method is that we're going to start at the initial condition, figure out essentially what the equation of the tangent line is, and move in the direction of that tangent line or the slope for a little step size. Then I'm going to figure out what point I'm at and do it again. Now I'm standing at this point. I'm going to move in the direction of the tangent line for that little bit of step size, calculate my new point. I think it's easiest to do Euler's method and to like kind of keep track of what's happening using a chart or a table. So here's what my table is going to look like. I've got the x that I'm on right now and the y that I'm on right now. And then I need to know my new y value. So right now my x is starting at 0 and my y is starting at 1. Well, to get my new y value, this is really just that linearization equation or the equation for a tangent line that says what y value am I at right now plus move in the direction of the slope for a little bit of a change in x. So to get my new y value, I'm going to take the y value I'm at. I'm going to add to that, evaluating the slope at the point. Well, I don't have to take a derivative because my differential equation has already given me the derivative. In order to find that y prime piece, I just have to plug my point in. So if I plug in 0 for x and 1 for y, then I get a slope of 1. Because it's like 1 minus 2 times 0 squared. And then I'm going to move for my little step size of 0.25. This one I can do. I think we can probably do 2 iterations of this and then I'm out without a calculator. So here, 2 times 0 is 0. So that's 1 times 0.25. So I'm now at 1.25. So now I've taken a step in the x direction, and my step in the x direction was that step size of 0.25. And I've ended up at the new y value of 1.25. So now I'm standing at this point right here. And there's a question in the chat that I think is related to my handwriting more than anything else. So let me scoot this over a little bit, but that 1 is the y sub n. This part is my derivative, and the step size is delta x. Hoping that answers the question in the chat. So to get my next y value, I'm now standing at the point 1.25. I'm going to move in the direction of the slope. But my slope I'm going to get from the differential equation. So my y value is now 1.25. My x value is now 0.25. Which I need to square. And then all of that would be multiplied by 0.25. I can probably manage to do that without a calculator, but I think I'm going to punt. Joy, did you have a question?
Yeah, but I figured it out.
Okay. So this number that we get here, and I'm just, like I said, I could do that by hand, but I'm going in on the calculator. If someone beats me to it, you can just let me know what answer you got. But 0.25 times 0.25 times 2. So 1.33? 1.53. Cool. So now that I've got that new y value, that means I am now standing at the point 0.5, 1.53, which means I've actually answered the question. Because the question was to estimate y of 0.5, and I got there because I took 2 steps of the x, and that y value is my estimate. Yeah.
Why did he put the return value? Why did you put 0.5 instead of 0.53?
For the x value?
Yeah.
So my x value is always going to increment by my step size.
Okay.
So in the x direction, I'm always moving 0.25.
Okay.
The only part that Euler's method is calculating for us is the new y value.
Okay.
Phase plane is looking like this. And then we're asked to draw some solution curves. And I would argue we should, from this picture, be able to find and classify all equilibria as well. So I'm going to start with finding and classifying the equilibria on this one, even though we weren't asked to do this on homework 15, just letting y'all know. But if I were going to find and classify equilibria, the equilibria are happening. There's only one L in equilibria, but I always write it with 2, and I don't know. Sorry, it's already written. So our equilibria happen when y prime is equal to 0. So essentially the equilibria, those are the points that if we get there, we are stuck there forever. So I am looking at 1, 2, 3, 4 equilibria. And I'm just going to go straight into thinking about what my graph is going to look like at those equilibria. So if I start at a y value of -3, I am stuck there forever. If I start at a y value of -1, I'm stuck there forever. If I start at a y value of +1, I'm stuck there forever. If I start a value of 3, I'm stuck there forever. Now, back when we were doing this like as a phase plot sort of thing, anywhere that my curve is above the axis, I know those are places where my y prime is positive, which means y is increasing, which means I'm moving to the right. So I'm moving to the right in here, I'm moving to the right in here, and I'm moving to the right out there. Anywhere that we are below the axis, those are the parts where we're moving to the left, because we are moving towards smaller y values. So if I look at this, -3 should be stable equilibrium, unstable, stable, unstable. Well, now let's move down to what our graph's going to look like down here. In all of these places where I am above the axis, where my derivative is positive, I know that I have positive slopes. So I know that if I were drawing a slope field, between -1 and 1, I need to have all positive slopes, right? I know that above 3, I need to have positive slopes. I know that below -3, I need to have positive slopes. And in between the other direction, I'm going to end up with negative slopes. And if I go to graph some solution curves, I know that if I start out between -1 and 1, I get pushed towards 1. I know that from looking at the phase plane. So getting pushed towards 1, my curves are going to do something like this. If I start out between 1 and 3, I also get pushed towards 1. So if I start out in here, I'm going to get pushed towards 1. If I start between -3 and -1, I get pushed towards -3. So I'm headed down towards -3. If I start off less than -3, I get pushed back towards -3. And if I start above 3, I get pushed just bigger forever. Now, the question of what happens, I normally don't say this about Chalonor's homeworks. I usually think they're pretty well written. I don't like the fact that he says what happens to the solutions as t approaches infinity. I know that he said it depends on your initial condition, but it like really depends on your initial condition. So there isn't one answer to that question. I will say that he phrases it a little bit better in the practice exam, when he gives us, is that what I was looking at? Practice exam, homework, I don't know. I was looking at something where he gives us specific initial conditions to look at. And if he gives us specific, oh, right, number 8 on the practice midterm. If he gave you a specific initial condition, then we can answer that question of what's happening as t approaches infinity. So for example, if I gave us the initial condition that y of 0 is equal to 2, then the limit as t approaches infinity of y, if I start at 2, I'm going to get pushed towards 1 for a final answer. If my y of 0 was equal to 4, then the limit as t approaches infinity of y would go to positive infinity. If I go ahead and solve for our equilibria, I'm always starting in the same place and setting y prime equal to 0. Well, I gave us something that factors. So I can pull the y out, and then I'd have a minus y here. So I know that I should have equilibria at 0 and at A. Personally, I think in graphs. So when I see this, I'm really thinking about, if I'm being asked what conditions must be placed on A, I'm thinking about kind of what are the ranges of A values we might be looking at. Well, if A is 0, then there's actually only one equilibrium. And then we can think about that A being positive or negative and whether that changes anything. So I'm going to graphically think about that, and then we can also use the stability criterion to think about it. So I'm going to start with graphical and see what would happen if A was 0. Well, if A was 0, then my y prime would just be negative y squared. Which means if I were graphing this phase plane, everything's below the axis, everything is headed to the left, and 0 is actually semi-stable because it's stable from one side and not from the other. Yeah.
How do we get y prime is equal to negative y squared?
So if I plug in 0 for A, then this piece is gone.
Okay.
Right? Like I'm literally having to try different values for A to see what's going to happen. So if we pick now, if I think about letting A be positive. So if A is positive, then my curve is kind of shifted over. And now if I'm looking at my phase plane stuff, I'm going left, I'm going right, I'm going left. So this one works. That's stable. And now let's check what happens if A is less than 0. So if A is less than 0, I'm going left, I'm going right, I'm going left, which means this is not a stable equilibrium. So the criteria that have to be placed, or the condition that has to be placed, is that we need A to be greater than 0 in order to make this stable. I don't know if that completely got at what you were hoping to work through. If we were going to do this off of the stability criterion, we could work through it that way also. I have unfortunately run out of space on my page. Squeeze it in over here. I'll squeeze it in over here. So if I were going to do this based on the stability criterion, that means that I'm going to look at my differential equation. I'm going to look at my y prime and I'm going to take another derivative. So I'm going to take the derivative of my y prime equation. And if I do that, I'm going to get a minus 2y. So if I plug in my equilibrium of A for Y, then I would get A minus 2A, which would give me negative A. And in order for this to be stable, I need this to be negative. And it's only going to be negative if my A is a positive number. And we are finding the area . So in general, I got to draw pictures. So I know that we're only looking at the y equals 0. So I know I'm going to be bounded by the x-axis. 1 over x looks like that. X squared looks like this. And now that x equals e thing is going to require a little bit of effort to figure out. So I can just look at these and see where 1 over x is going to be equal to x squared. What number can you plug in on both sides to make them the same? Yeah. So these are going to intersect at x equals 1. If you wanted to do math for that, you could. You can multiply both sides by x and then take the cube root of both sides. But we're going to get back to 1. So that means that this point right here is at x equals 1. E is about 2.71828459045. I could keep going, but I'll spare you. E is about 2.7. So it is somewhere over here. So no matter what you do to find this area, we have to break it up into 2 pieces. So this region, I could try to go left and right, but I've got different left and right walls. If I go top and bottom, I've got different ceiling and floor functions in different parts. So I have to break this apart right here and write 2 separate integrals. Over on this left-hand side, I know I'll be looking at the integral from 0 to 1. My top function is x squared. The bottom function is y equals 0, and it's totally fine to subtract 0 on there, but we don't actually need it. So y equals 0 is the x-axis. So the only part that has all 4 of these as walls is the part down here. Anything else wouldn't have all 4 as walls. Yep. So I'm going to have to add that to the integral from 1 to e. And over here, my top function is 1 over x. My bottom function is 0. Again, you do not have to write the 0 part if you don't want to. He was pretty nice to us numbers wise. So if I integrate that, I get 1/3 x cubed. I'm going from 0 to 1. So that's 1/3. Technically minus 0. I'm going to skip the minus 0 part. Over here, when I integrate 1 over x, I get natural log absolute value of x. That's going from 1 to e. Since all the numbers I'm plugging in are positive, I didn't really need the absolute value. But that's going to look like ln of e minus ln of 1. Natural log of e is 1, and natural log of 1 is 0. So my final answer here is 1/3 plus 1, or 4/3. If I'm drawing this picture, I've got y equals x squared. And 2 minus x means I've got a y-intercept of 2 and a slope of -1. So it's going to come down like this. And so the region that's bounded by these two curves and also y equals 0 is this little almost triangle thing down here, because that's y equals 0. So we're, yep. Well, on the left, there's no region that's bounded by those three things. Right? Like this means that these three things are going to be like the 3 walls of the little room we're looking for. So there isn't a region over here bounded by those 3 things. Right. It wouldn't be bounded. So we're talking about this little room in here. So if I imagine making myself really, really small and sticking myself in this little room. I swear I put my glasses on. Don't worry. Okay, so I'm really small and I'm inside of this little room. And if I'm standing right here and I look up, then the function I see for the ceiling is the line. But if I were to scoot over here and put myself in this part of the room, oh man, I got to get even smaller over there. But if I put myself in this side of the room and I look up, the function I see on top is the x squared. That's really how I know that I have to break this up into 2 pieces. So visually on the graph, I know I'm going to break it up right here. So that means I need to figure out what this x value is. And I need to know what this x value is in order to set up my 2 integrals. To find this one that's happening at the intersection point. So I can set my 2 functions. I can set the line equal to the parabola. And I think I have chosen something that factors. So if I rearrange this a little bit, so I've got x squared plus x minus 2. I think that's going to factor as x plus 2, x minus 1. Which means these intersect at -2 and +1. And based on my picture, I know this is the +1. The -2 would be over here, but it's not in the region we care about. To get this point, that's actually the intersection of the line 2 minus x and the other line y equals 0. So if I were to set these 2 equal to each other, that's just going to give me that x is equal to 2. So when I set up my integrals, I know that in the left-hand region, I'm going from 0 to 1. And I know that in the right-hand region, I'm going from 1 to 2. There is a way to set this up to only have it be one integration, but it would require me taking my slices horizontally or going left to right and doing it as a dy. And I don't want to. So I think this is easier than doing the work to switch this around to be a dy. Depending on the problem, I may make a different choice. This might get really messy because I'm not sure how to find the intersection points, and I was trying to find something where the intersection points were nice, and then I was struggling with in my head. So we are going to set this up, but not necessarily finish it off, but just to illustrate another one where I might have to split it up. All three of these are reasonable to ask you to graph. What I do not think is reasonable is asking you to find the intersection points for a couple of these. So y equals e to the x, we should know has a y-intercept of 1. 3 minus x, we should know has a negative slope and looks like this. And y equals 1 looks like this. This intersection point is reasonable for us to find. This intersection point is not reasonable for us to find algebraically. So I'm going to find this intersection point for us. You're going to find that intersection point for us. I found this one. This one's 0.8. Did anyone find the other point for us? That's what I got also. Yeah. Yep. There is no way to algebraically solve for this. That is why I did it for you. He would not ask you to do that. I had to use Desmos to get a numerical approximation. Yeah. So now that we have those numbers, go ahead and set up your two integrals. Pick it up right here in this region. So I know I'm integrating from 0 to 0.8. And over here, my top function is e to the x, and my bottom function is 1. In my region over here, I know that part is going to integrate from 0.8 to 2. My top function is 3 minus x, and my bottom function is 1. I don't know why I wrote a y over there. Just because I can or something. So let me fix that.